All right, so I just want to go over. Remember, yesterday we talked about the fundamental theorem of calculus. We learned that this is the formula for it. Okay, and once you get it to this point, you have to plug in your b value and your a value and subtract them. And that'll give you your value for the integral. Now remember, the integral also means that you're finding the value of the area underneath the curve of what you're integrating from point A to point B, right? So anytime you do integration, always think of it as area as well, because it might kind of make some word problems make more sense, right? They say find the area below the following, you know you should be integrating. But just as a real quick review, let's try this out here. So example number 1, I'll give you a couple minutes maybe to try this out. Okay, but do this. And then example 2, I'll put it over here to the side of it. Try this out. So let's do integral from 0 to pi over 4 of cosine of x dx. So I'm going to kind of stop the time, the recording real quick. I'm going to give you guys a minute or so. Try to do these. All right, so for the first one, we have to integrate x squared, right? So you're going to get x squared, and you're going to add 1 to the power, so it's x cubed, and then divide by the new power, so divided by 3, and then from 2 to 3. Now remember, you plug in the top number first, so it's 3 cubed over 3 minus 2 cubed over 3. So that's going to give you 27 over 3 minus 8 over 3. So your answer is going to be 19 over 3. Again, this is your solution or the area underneath the curve of x squared. And remember, you guys can put this into your calculator and do that as well, right? Just to double check your answer. You can do it graphically or just by going to the integration command in your catalog. So for example number 2, we're going to integrate cosine of x. So what's the integral of cosine of x? Sine of x, right? So sine of x, and that's from 0 to pi over 4. So when you plug it in, you're going to get sine of pi over 4 minus sine of 0. So sine of pi over 4 is radical 2 over 2, and sine of 0 is 0. So your answer will be radical 2 over 2. So hopefully you guys don't see definite integration as something that's like crazy difficult. It's basically the same thing you're doing. You're going to integrate, but then you're just going to plug in some numbers to find the actual value. Notice there is no plus c's, right? Because we're actually finding an exact solution. We're not just finding a general solution. We're finding an exact solution. So no need to put the plus c. Okay? So like I said, we're just going to do a couple extra examples. So there you go. Now let's talk about the mean value theorem for integration. Okay? So the mean value theorem for integration. But before we do that, just a real quick recall. The mean value theorem, so MVT, mean value theorem for derivatives. I'm going to put right here, for derivatives. Now we normally don't call it the mean value theorem for derivatives, but right now I'm just putting it there, is f prime of c equal to, and then we put f of b minus f of a over b minus a. That's the mean value theorem for derivatives. We're going to do the mean value theorem for integrals. So mean value theorems, the NVT, for integrals. Now this one we do tend to call it the mean value theorem for integrals, or else we might call it the average value theorem. I keep misspelling that. Okay, and it's more common that we call it the average value theorem. Okay, and actually, average value, the word value is kind of dynamic because this right here isn't normally the thing that we say. We might say the average temperature, find the average temperature, find the average slope, find the average rate of change. The word average means you should be doing the mean value theorem for integrals. Okay, so that's a big clue. Okay, so this word right here, huge clue as to what we're doing. Okay, sometimes they will say average value, sometimes they won't. So I guess I can highlight the other one with a different color just to kind of say like this is important too, but usually the main word average is the key. Okay, so the average value theorem is given by this formula. So average value is equal to 1 over b minus a times the integral from a to b of f of x dx. Now, the way they got this, and I don't know if it'll make a lot of sense to you guys, but let me just kind of show it to you really quick. But here's how they got this formula. Remember the mean value theorem for derivatives? Okay, here it is. They said, let's integrate both sides. Okay, now when they did that, what's the integral of a derivative? What happens when you integrate a derivative? It kind of disappears, right? So notice that will become f of c. So there's your average value, okay, your answer. Now, the b minus a, that's just a constant, guys. This is just 1 over b minus a integral of f of b minus f of a. But what does this kind of look like? If you're integrating the process of f of b minus f of a, like, does that look like this from a to b? I'm sorry, a to b, right? And if you integrate the original problem, you end up with just this function right here. So this is how they ended up with that. Okay, so it's not like, oh, they just created something. They actually integrated the mean value theorem. Now, you don't have to know where this all comes from. Okay, I'm going to actually erase it because I don't want it to be in your notes and you're thinking, did we do a bunch of work for this? No, I'm going to erase this stuff. But I just want you guys to see that the way they got the average value theorem is they just integrated the mean value theorem for derivatives. Okay, and they worked their way around it just to get the solutions they needed. Okay, so that's how they went about and got that value. Okay, so what we're going to do is we're going to try to find the average value. Okay, we're trying to solve for f of c, right? Like what I showed you guys earlier, or we call it the average value. So let me give you an example of how this works. And they're not hard problems. They're actually, these problems actually pretty much come out once, maybe twice per AP exam. Okay, and they're not difficult to do. So here we go. Find the average value of f of x equal to 3x squared minus 2x on the interval. And by the way, right now as I'm writing this, this is another clue. Whenever they say to find the mean value theorem over the interval from 1 to 4, so that kind of sounds like, oh, you want me to go from like 1 to 4, like I got to figure this whole area out. So that should be a big clue as well, that you're integrating whenever they say from the intervals of A to B. Okay, if they ever tell you that, that's a big hint. All right, so let's go ahead and figure this out. So average value is equal to 1 over b minus a. So my b value is 4 and my a value is 1, right? So I'm going to put 1 over 4 minus 1. Integral from 1 to 4, right? It's an integral from a to b of f of x dx. Well, f of x is 3x squared minus 2x dx. Well, my fraction is going to be 1 over 3. Okay? And then I'm going to integrate. So 3x squared becomes 3x cubed over 3 minus, and then the next one is 2x squared over 2. From 1 to 4. I'm just using the power rule, right? I'm adding 1 to the power and dividing by that new power. Okay, so I'm adding 1 to the power, dividing by the new power. So let's go ahead and plug in the numbers. 1/3. Actually, you know what? Let me rewrite this. X cubed minus x squared. I just realized I could simplify it. So 1/3. 4 to the third minus 4 squared minus 1 to the third minus 1 squared. Remember, you plug in the 4 first into the whole expression, and then you plug in the 1 after. Make sure you subtract in between. So this will be 1/3. 64 minus 16 minus 1 minus 1. So that's 1/3. Well, 64 minus 16 minus 1 minus 1, that's basically 64 minus 18, right? So we end up with 48. So this becomes 48 divided by 3, which is possible. You can divide 48 by 3. That gives you 16. So that's my average value. So notice you're just basically plugging in the information into a formula and working it out. Okay? And if you think like, oh, that wasn't so bad, the AP ones really aren't that difficult either. Sure, they might give you some like complicated looking variables to work with, but if you feel confident with your integration, the average value problems are easy. They're usually very easy, even in the AP test. Okay, they're kind of like gimme problems. Anytime you see them, you should see it like a gift. Like, here's 3 points I'm going to get for sure. Okay, so any questions on this? Right now we're going to go over the second fundamental theorem of calculus. Go ahead.
Shouldn't it be 46?
Did I?
Because 64 minus 16 is 48.
And minus... Oh, you know what? Hold on. I didn't transfer this properly. Hold on. I did it in my head, but not here. Here's the error. I'm going to put it in red. This should be a plus. That should be a plus. I didn't distribute. By the way, there is a book out there called The Most Common Mistakes in Mathematics, and the number one most common mistake is distribution of a negative. A lot of times we forget to push it over. So I got rid of the parentheses, but I forgot to change that minus to a plus inside. So yeah, so that cancels itself out. Thank you for that. Even though I was right, I was still wrong. I got the right answer, but I put the wrong sign. So, all right, second fundamental theorem of calculus. And this is just going to be one example as well. But let me give you guys the second fundamental theorem of calculus. All right, so the second FTOC, right, second fundamental theorem of calculus, says if f is continuous on an open interval I containing A, if this freaks you out when they say interval I, you can write open interval A to B. Same thing. They're just not trying to write A to B. Also, containing A, you can just say containing C. You can change this up however you want. Then for every x in the interval, we get the following. d dx of the integral from a to, I don't want to call it x, let's call it f of x, of f of t dt is equal to, you know what, maybe I should call it, hold on, erase that f of x on the upper limit, let's just call it x, and I'll make sure that I make it clear right now, but we'll just call it x. From a to x of f of t dt is equal to f of x times d dx of x. All right, the main thing is this. The thing that happens with the second fundamental theorem, I'm kind of highlighting it up there. You're going to notice you're going to take a derivative of an integral, but that integral is going to have a constant on the bottom. Now, a can be positive or negative, doesn't matter. It can be pi over 4, who cares? It's just a constant. But you're going to notice that its upper limit is an expression, x squared, sine of x, or just an x, okay? And what you do, if you want to think of this in the sense of a shortcut, is you get this variable and you plug it in right there. That's how we got f of x. And ignore the rest because the derivative gets rid of the integration part. So you're going to get the expression and plug it into the function, okay? And then you take a derivative of that upper expression, okay? So you're going to take a derivative of that upper expression. I have two examples to kind of show you guys as to how this works, okay? So let's go with, I would say, an easier one. This is example 4, I think. Maybe I'll do 3. When do we get out of here? Oh, what?
8 minutes.
8 minutes? Okay, so we'll try doing. All right, so let's try this really quick. Evaluate d dx of the integral from 2 to x of t plus 1 dt. So this is like an easy problem, and then we'll kind of make it a little bit more difficult. So, since I'm taking a derivative of an integral, but the upper bound is an expression, then I must use the second fundamental theorem of calculus. So this is what the second fundamental theorem of calculus tells me to do. Get this and plug it in wherever your variables are supposed to go. So I'm going to write x plus 1. And then I have to take a derivative, so times d dx of that expression. Well, what's the derivative of x? 1. So then you just write x plus 1, and you're done. Okay, because d dx of x, this right here, is equal to 1. So then it's just x plus 1 times 1. So it's just x plus 1. Okay, we'll do another one kind of easy like that. Then we're going to do one that's a little bit more tricky, but not terribly tricky. Example number 5. I want to evaluate d dx, the integral from -3 to x of secant squared t dt. So notice, derivative of an integral with an expression as an upper bound. That's second fundamental theorem of calculus. So first thing you do, get that variable and plug it in. So that's going to be secant squared x times the derivative of my upper bound. So what's the derivative of x again? It's 1. So what's my answer? Secant squared x, right? Okay, no big deal. The only time this becomes interesting is the next example. So example number 6. And this is the last thing. Find the derivative of the integral of 2 x cubed plus x of 1 over t squared dt. Don't let the fact that it's a fraction scare you. Don't think like, oh man, now I got to move that fraction up. No, no, no. All you got to do is plug stuff in. Okay? So they want me to find dx of the integral from 2 to x squared plus x of 1 over t squared dt. So what's my first step? Plug it in. Get that and plug it in. So it's going to look like this. 1 over x squared plus x squared. Because I just plugged x squared plus x where the t is. So x squared plus x squared. And then I have to put dx of x squared plus x. What's the derivative of x squared plus x? 2x plus 1 divided by x squared plus x squared. And there's your answer. So, all right, we're done. I will give you guys an assignment here in a bit. All right, so this was a 3, right, before? So I'm just going to change it to a 2 because I made a mistake when I was doing that. So we'll just write x squared plus x over 2, and everything else should be just fine. Here's your homework. So you're going to be on page 278. Numbers 13 to 22. Those should be pretty easy. All it is a bunch of areas, and they're saying to set up an integral that would depict the area that they're showing you. So that's all you're doing is just kind of writing down the areas of those shapes. You'll see them when you see in your book. Adding numbers 47 and 48. This is section 4.3. And page 293. 5 through 16. 51 to 56. 81 through 86. 89 to 92.
I think it's pretty.
Section 4.4.